sorry, turn on the video recording and start. So I'm trying to write half screen because I want to do half screen computations and half screen Scratch. It's already very dense. I hope it will work. So announcements for today. Homework 1 for those of you taking this class for Mark will be on the web by midnight. So just on the class website. I haven't yet figured out exactly how to do it, but by midnight I'll figure out. And I want to remind you what we did last time, and I want to do a little bit more of it today. Though the course is not computational, so I mean occasionally we'll have a computational class like last time and like today, but soon enough we'll switch to other theoretical things. So let me remind you, we invented a notation for knots. So basically, is this visible? So you mark the edges of the knot diagram. So 1, 2, 3, 4, 5, 6, and then in each crossing you list the edges around it going counterclockwise. Starting from the incoming lower strand. So this crossing will be x 1, 5, 2, 4. This crossing will be x 5, 3, 6, 2, 5, 3, 6, 2, and so on. And then we started writing a program to do the Jones polynomial to compute the Kaufman bracket. And I want to review the program, but also tell you that I spent some time and entered a lot of data for the program. Okay, just so that we can play with it. So I've entered 250 knots into the program. Okay, so here they are. So generally speaking, for the first for knots with up to 100 crossing, there is an agreed notation. And it's arbitrary, but it's agreed. So, and the notation is, you write n sub k, where n is the number of crossings, and k is the serial number of that knots in some agreed upon tabulation within the list of knots with n crossings. So there is 3, 1, and 3, 1 is the knot drawn here, the trefoil. There is 4, 1, and I could risk trying to draw it, but it would probably be easier for if you Google the figure 8 knot. Then there is 5, 1, and 5, 2, and so on. Okay? So, and maybe even 5, no 5, 3. But so I didn't print the knots for you, but here are their PD notations. So 3, 1, here is the notation for it. 4, 1, here is the notation for it. 5, 1, here is the notation for it, so on. And then the list goes on and 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 on. Oh, I'm sorry. I mean, just scrolling takes forever. Oh my God, I'm still at, now I'm at knot 10.6. I have to go to 10.165. Maybe if I use the, I'll just scroll. Sorry about that. Lots of knots. And then, but after that list of knots, so again, I've just entered them so that we'll have something to play with. And it's the standard so-called Rolfson table of knots. Yeah, that was a mistake. here we are. 161, okay, good. So maybe I should actually enter them into the computer, so let me evaluate this line. This does nothing, it just enters the computer notes into the computer, and then I've put two more notes and I just wanted to tell you about them. So one of them is the Gomf-Scharlemann-Thompson 48 crossing knots. You can see a picture of it. It should be a bit hard to decipher, but well, here you go. There is a picture. I also marked the edges, and here is the corresponding PD notation. So now it's a single knot, but its PD notation is rather long because it has 48 crossings. And the reason I'm showing it is because there is something called the ribbon slice conjecture, which people believe is false but cannot prove is false. And this is a proposed counterexample. So people don't know how to prove that it's a counterexample, but this may be a counterexample. We will at some point mention the ribbon slice conjecture, and I will explain what it says. At the moment, I only wanted to say sometimes you have a rather big knot. In this case, it's a 48 crossing knots, and you want to understand it. So I don't know, you want to compute various things about it. In particular, maybe you want to compute the Jones polynomial, and so I just wanted to show it. And then the last knot that I wanted to show is this one. So this is the 55 crossing Pizzerillo knot. Pizzerillo is Lisa Pizzerillo, who up until a year ago or so, or 2 years ago maybe, was a graduate student, I think in maybe Pennsylvania somewhere, or maybe I'm confused about the location. You can see her paper by going to archive 1808.02923. And in her paper, which was her thesis, she proved that the Conway knot is not slice. Whatever, again, a certain property that at some point we will understand, at the moment we don't. And for the proof, she had to compute the so-called Chovanov homology of this knot. Chovanov homology is a more complicated version of the Jones polynomial. So certainly we want to compute the Jones polynomial of a knot like this. So we'll try. Okay? But again, the problem with this one is it's big. It has 55 crossings. And finally, here is our blackboard from last time. I hope it's visible. I mean, there is very little I can do. Maybe I can enlarge it a bit. But there is very little I can do otherwise because I'm trying to split the... Sorry. Yeah, I can enlarge it a bit, but only a bit. So the key to the computation of the Jones polynomial was a transformation. Xijkl, so the notation for a crossing, became A times Pij pkl, where P just means a path from edge 1 from edge I to aj. So the zero smoothing is Pij times pkl because it's a path from edge I to edge j, and another path from edge k to edge l, and then plus A inverse times, or plus B times PIL PJK, which is the one smoothing. And then last time we didn't quite write a program. We only executed the program line by line. But then I went home and wrote the program myself, and here it is. And since this is not a programming class, and what I want to emphasize is other things, I'll go through it very briefly, and please don't feel uncomfortable if you don't really understand the syntax. The syntax is not, or of this programming language, or the details of this programming language. The details are not what I really want to concentrate on. I want to just have a view of how to compute things. Okay? By the way, the new people who just joined, if you can join with video, it's better. You don't have to, but if you can, it's better. Okay, so given a PD, which is so the program is called KD, Kaufman bracket, and it gets an input, a PD, so a planar diagram, a notation along like this. The program has several local variables. They are P, so P is the thing that I use to indicate smoothings, and then T1, T2, T3, T4, B and D. Okay? And then the program works as follows. First of all, there is a technicality here that I want to skip. And then there is the variable T1 is said to be the PD to which you apply the transformation xijkl goes to A pij pkl plus B pil pjk. This is precisely the Kaufman relation. This is somehow the key mathematical point. Then you expand this, so from a product, so if you're talking about a 7 crossing knot, then T1 will be a product of 7 sums of 2 things each. And if you expand it, it will become a sum of 128, 2 to the 7 factors, each of which is a product of 7 things. So this is T2. In T3, you simplify long edges. So again, we talked about it last time, but I'll remind you. So if you have a long edge, if you have a long edge which has 2 points in the middle, so I, J, K, then one notation for it is Pij, P, J, K, and another notation for it is P, I, K. And I prefer this notation because it's simpler. So I tell the computer that T3 will be T2 to which you apply the transformation, Pij, Pjk becomes Pik. Then T4 counts loops. So once you apply this transformation, it turns out that there are only 2 types of loops. There are loops that have one dot on them, and therefore both sides of the dot are labeled I, so they look like a PII. And then there are loops that have 2 dots on them, and one side is I, the other side is J, and then such loops are Pij squared. So the program looks for PIIs and replaces them by D, and looks for Pijs and Pij squared and replaces them by D. And then the final thing that the program does is, okay, so now you get the Kaufman bracket in the variables A, B, and D. But B is just 1 over A, so I make the substitution, and D is minus A squared minus 1 over A squared, so I make that substitution too. And I enter the program into the computer, and now it's ready to run. Any questions, any comments so far? So again, you should at least loosely understand. If you don't know the programming language, I cannot expect you to fully understand, but you should at least loosely understand what's going on. Do you?
Just a quick question about the PIJs. Does the set attributes P orderless just mean that we're not distinguishing between Pij and Pji?
Yes.
Okay, great, thanks.
It means that I want those edges to be unoriented. That's the only, yes, that's what it means. Okay? So, example, let's look at the knot 817. So maybe I should have done this. So I'll type knot 817. It's a knot with 8 crossings. 1, 2, 3, 4, 5, 6, 7, 8. I could draw it for you, or you can Google it. But that's not what I want to do. I just want to compute its Jones polynomial, its Kaufman bracket, whatever it is. So I execute the next line, KB of knot 817, and very fastly, I don't think fastly is an English word, very quickly you get an answer. This is the Kaufman bracket. Now, this isn't the Jones polynomial, you can complain, okay? To do the Jones polynomial, I have to multiply by negative a to the negative 3 raised to the right of the naught. I could put it into the program. But somehow I decided that the cost is not worth the benefit. So the cost is a few more lines of code, and the benefit is almost nothing. Because computing the right of a knot is something that you can do by hand. Computing the Kaufman bracket is very difficult. You'll see how difficult in a minute. But computing the right is, you just count the crossings, each one with its sign. So you go, you have your knot, you go 1, 2, 3, 4, 5, and you check the sign of each one. I mean, this is something that it's not worth to program. Okay? And then the Jones polynomial also involves the substitution. A goes to to q to the negative 1, 4 or something. But again, if you have a to the 18 and you want to substitute a is equal to q to the 1 over 4, I think you can figure it out. Okay? This is so easy that it's not worth implementing. So essentially we've computed the Jones polynomial of 817 up to technicalities, minor technicalities. Are you okay? So the next thing I want to do is I want to tell the computer to make a table of KB of not 10 sub k, where k goes from 1 to 165. So there are 165 10 crossing knots, and just to test the program, I want the computer to compute the Jones polynomials of all of them. And for each one, I also compute the timing that it takes, and I echo the result, so I print the result, okay? And then I save this table as a variable called KB on 10. So let's see what happens. 10 crossing, test 10 crossing, 10 crossing. There should be 165 of them, so it will take some time, right? So this is knot number 11 of the 10 crossing knots. It took 0.9 seconds, and the result was this. And it goes on and on and on. Why is it so slow? Right? I mean, we're actually talking to computers. Computers can do things quickly. So it's slow for two reasons. One reason is that the language I'm using, well, for three reasons. One reason is that the language that I'm using is very expressive, so programs appear short in it, but on the other hand, it runs very slowly. The second reason is that the program is lousy, and that's what I really want to talk about today. It was very short, but it's lousy, okay? And the third reason is that it's a difficult computation. If you have n crossings, you have 2 to the n smoothings. 2 to the n grows exponentially. Things that grow exponentially are slow. Okay? So, well, it's still running. It's still running. It will finish eventually. And how far are we? I mean, I actually, we are in knot number 89 out of 165. You know what? Maybe I'll interrupt that because the point was made. So I've interrupted the computation. Believe me, it's going to take about 3 minutes overall. Okay? So I'll skip the next line, which was supposed to be computing how long it actually takes. Believe me, it's about 3 minutes. I think you should believe me. You've seen roughly how it goes. Next, there was this Gompf, Sharman, Thompson knots that I cared about, which has 48 crossing, which is even less than the Picirillo knot that has 55 crossings. And let's see how long it takes to compute this one. Maybe we should estimate, okay? So if 10 crossings, the average 10 crossing knot took about a second, actually a bit less than a second, but okay, let's call it a second. And this involves 2 to the 10 computations, 2 to the 10 smoothings. This involves 2 to the 48 smoothings. So the number of smoothings is 2 to the 38 more. 2 to the 38 is 256 giga, right? It's about 300 billion. So this should take about 300 billion seconds. 300 billion seconds is how many years? 10,000 years?
8,000-ish years.
Yeah, 10,000 years or
seconds is
so.
about 30 years.
What?
A billion seconds is about 30 years.
Right, so but that's, what did we say, 300 billion? Okay, you know what?
So yeah, 10,000 years.
Clearly class will end before we're done. Okay, so I'll interrupt this computation, but not before telling you that Lisa Picirillo actually computed the Chovanov homology, which is harder than the Jones polynomial, for a bigger knot, the 55 crossing knot. So there must be something better that can be done. Okay? By the way, she used my program. Anyway, or programs that an undergrad written under my directions a few years before. Anyway, so here is a faster program, FKB, to compute the Jones polynomial, and I want to explain how it works and philosophically why it works faster. Okay? So, so that happens on the math side of the board. So the problem is that I really need a large knot, or a rather larger knot, to demonstrate it. So let me draw a schematic knot. So here is a schematic knot. Okay? I'm not bothering to indicate the signs of the crossings, right? Which one is over, which one is under. Some knot that looks like this. So the idea is not to smooth everything at once. If you smooth everything at once, you you have to consider, so how many crossings are there here? Maybe 10 or so. So you have to consider 2 to the 10 cross smoothings, and 2 to the 10 is a large number. Not to mention if that was 48, so then it would be 2 to the 48. So instead, you draw a horizontal line through the knot, actually not passing through a crossing. So the horizontal line I drew was bad. Anyway, you draw a horizontal line through the knot, and you smooth only the crossings below the line. And the ones above the line you save for later. But if you smooth only the crossing below the line, only the crossings below the line, well, I mean, now maybe half of the crossings are below, so I have to look at 2 to the 5 smoothings, which is a lot less. And many things will simplify, because, for example, over here, after smoothing, possibly I would get a loop, right? This loop will simplify to a D. So, basically, all the loops below the line simplify. So the only, or get replaced by D. So the only things that end up remaining are arcs that are not closed loops. What does it mean not to be a closed loop? It means that they are arcs that start at the blue line here. Let's give this blue line a name. So let's call it the front. In a minute you'll see why. So basically you get curves, non-intersecting curves that start at this blue line and end at this blue line. So maybe, you know, a curve like this, I'm not, no, you know, maybe I should try to follow the strands of the knot, because they actually do follow the strands of the knot. Where is the undo? Here. I don't know, maybe you'll get this, and then that, and then this, and then that. Okay? But, and then such a system of curves will come with a coefficient which comes from all the loops that were created and all the A's and the B's. Okay? Now, so the value of what you see below the front is basically, I need another page. Sorry about that. Page, append, go. Good. So the value of what you see below the front, so let me draw the front, and the value of what you see below the front is a system of curves that begin and end on the front and are otherwise non-intersecting, and they come with a coefficient which involves A's and B's and D's, but B is a function of A and D is a function of A, so it comes with some coefficient which is some Laurent polynomial P of A. Okay? But now the point is that there are relatively few such pairings of points along the front. It's actually a lovely exercise to figure out how many, but there are relatively few. So all you have to manage below the front is a relatively small number of pairings and coefficients which are Laurent polynomial, relatively few Laurent polynomials. So now, what is the new algorithm? So the new algorithm will be to again, let me start with the knot. So here is, well, it's not the same knot, but it doesn't really matter. So you start with the knot, you draw a front at the bottom, which, okay, so video is back on, and I'll stitch the two videos. It will appear funny, but thank you for noting this. So again, what is the strategy? I have a front, and I think of it like a weather front. It moves across the knot, okay? So I pass it over the first crossing. Then I pass it over the second crossing. Then I pass it over the third crossing. Then I pass it over the fourth crossing. Then I pass it over the fifth, and so on. So I raise it slowly. At each time, I compute what's below the front, and then to move the front one step, I only have to add one crossing. Okay? So the way this looks is, again I need to create a page. Sorry, I'm not learning from one class to the next. I was supposed to just create lots of pages in advance, but well, eventually I will learn. Let me create 5 pages now. Okay. So, so basically, after the first, or after a first few computations, or the first few steps of the computation, I have the front, and below it, I have a linear combination of smoothings. I don't know, maybe this smoothing, and each one comes with a Laurent polynomial coefficient. And then I introduce another crossing, so maybe the next crossing would be a crossing between these two strands, between strands that end at these two endpoints. So I'll end up adding either this or that. And each one will change the smoothing which is below, either by, well, switching it to a different smoothing, or by, for example, if I connect here a smoothing like this, it will create a loop which will give a factor of d. Okay? But anyway, whatever it is, it's a relatively simple thing, and it allows me to raise the front one step more. Okay? So here is the implementation. So fast Kaufman bracket of a PD is again a module, and the module has several local variables as before, and the new one calls KB. KB is the Kaufman bracket as computed below the front. So basically, KB stands for whatever is computed below the front, and the aim is to raise the front all the way up, and then KB will be the computation of everything. And it has a second local variable, to do, and to do is the part of the diagram that is above the front. Okay? It's what I still have to evaluate. And then I begin with setting KB to 1. So KB is 1 if the front is below the whole thing. And to do is the whole picture. And then, while the length of the picture is greater than 0, so long as I have work to do, so long as there are crossings to do, I let X be the first crossing in to do. And then to do is reset to be I delete X from to do. And then I run the exact same procedure as I did before. Namely, I set T1 to be KB. KB is already a product of smoothings. So I multiply it by the crossing X to which I apply the rule, the Kaufman rule. That Xijkl goes to A, Pij, basically the same Kaufman rule as before. Then I expand it, then I simplify paths, then if I find loops, I replace them by D, then I expand the end result after making the usual substitution, and that's the new value of KB. This gets evaluated again and again and again until there are no more crossings to add, and KB is the output. Okay? So, again, it should be, I mean, you should not understand the syntax, but you should understand what's going on. Is it understandable what the program is going on? Again, basically, it does exactly what I said. So anyway, yeah.
Hello. So the program takes the crossings one at a time.
Yeah.
Oh, okay. Is there a way to maybe make it see all the crossings at once? Or?
No, but that's exactly what I don't want to do. If you smooth all the crossings at once and you have 50 crossings, you have to look at 2 to the 50 cross smoothings. Instead, I put them one by one, and after each one, I simplify the paths and I make loops disappear. Okay? So let's do it. So let's run it on 817 as a test. I hope it's the same answer as before. That's just to see that the program is still the same program. And now I run the same program, the fast Kaufman bracket program on the 165 10 crossing knots, and let's see how long it will take. I mean, before it took about 3 minutes, except I stopped it in the middle. And how long will it take now? Well, did anybody measure? I don't know, but anyway, if I'll add all the results, in particular it will add the timing results. So the timing was 13 seconds, 12.9 seconds. That's a vast improvement, but it's still not good enough. If I wanted to run it on a 48 crossing knot, I've only improved by a factor of what, 10 or 15 or something. That's definitely not going to do. So next comes the next idea. So this is the program Extra Fast Kaufman Bracket, EFKB. So, so here's the idea. So I'll be more careful about which crossing to add. Why? I'll be careful about my choice of which crossing I'm adding next. Okay? Why? So what makes FKB fast, I've already explained. But what makes it slow? What slows it down? So basically, what slows it down is that if you have a front, here is the front, and it intersects the knot with a number of points, always an even number, then what the program will have to manage all the possible smoothings that involve, well, in this case, 6 points. How many smoothings are there that involve 6 points, right? Each one will come with a coefficient which is a Laurent polynomial, but sort of the thing that grows quickly is the number of smoothings, right? Because there is this smoothing, sorry, this one I did not between 2 endpoints, so there is this smoothing, then there is this one, I forgot to switch colors, it doesn't matter, but there could be a large number. In fact, if you've heard of the Catalan numbers, how many of you heard of the Catalan numbers? Okay, so the number of smoothings grow like the so-called Catalan, this N was not necessary. So it grows like the Catalan number Cn, which in itself grows rapidly, or as a function of n, the number of endpoints. Okay? In fact, sorry, it grows like it's C of n over 2. So it grows like n over 2. So it grows, but still it grows rapidly as a function of n. So what you want to do, if you want to make the program faster, what you want to do is to try to make the front as narrow as possible. You want to try to make the front not be too long, not intersect the knot in too many places. Okay? So...
I have a question.
Yeah?
Why the possibility of many different smoothings has already been I mean up to that point it is the polynomial is the sum of many smoothings. Are you saying like having many summons in the polynomial is going to slow the program down?
Of course, because you have to manage many summons. If you have to manage a billion summons, and then for each of the billion summons, you have to add another beat to the smoothing and play with it a little bit. And I mean, the program will have to run at least a billion steps. So I want the number of smoothings to be small so that the number of things I have to manage will be small. Okay? So anyway, so how do I, okay, so now here is the next thing. So again, here is the front. There is some number of endpoints ending on it, right? So it connects down to the rest of the knot below. And there are lots of crossings above. Okay? Which crossing do I want to add next? So the crossings that I add might be a crossing that crosses two lines that just came out of the front. So it might be a crossing like this. Or it might be a crossing in which a line that just came out of the front crosses a line that's that doesn't touch the front, that stays above the front. Or it might be a crossing in which sort of an arc connecting two lines on the front crosses the edge between the edge between them. So of these three possibilities, and there are actually two more, but I mean of these three possibilities, which one is best for me? So the new front will move over either to here or above here or above here. If I move over here, the length of the front remains the same. There were 2 points below and 2 points above. If I do this, the length of the front shortens by 2, right? It was 3 before and it becomes 1 after. And if I add this crossing, the length of the front becomes longer by 2. So the moral is, I want to add to the front the crossing whose edges come into the front the most. So every crossing has 4 edges emanating from it, and so these 4 edges might go into the front or somewhere else. I want to add the crossing for which the largest number of edges go into the front. Because, well, here the number is 3, here the number is 2, here the number is 1, and the larger this number is, the shorter the front is after after I add that crossing. So that's what the new program does. Everything is the same, except I have a new variable called front. Before, the front itself was only in my mind. The program before, the front itself was only in my mind. Okay? But now I actually want the front to be a list of edge numbers. I want to know what is the front, so that so as to choose which crossing to add. And then I do the same. So I start with the Kaufman bracket being 1. The to-do is just the PD. The front starts empty. I define the value of a crossing to be the length of the intersection of the front with the edges emanating from the crossing. So this length of an intersection of the front with something. And then while the length of to-do is too much, I choose the maximal element within the to-do list which is maximal by the value. The value is this length. And in fact, there might be several, so in between them I make a random choice. So that was the key point. This is the key point. Instead of the next crossing being the first one that comes to my mind, I choose the one which keeps the front as short as possible. Then then the rest is exactly the same, except that I have to update the front. Once I've chosen a crossing, the new front is going to be the complement of the, it's some set theoretic thing where you add to the front all the new elements, all the edges in X, and then subtract it's some set theoretic thing. Basically, the new front is the old front union the edges around X, but subtracted, I don't know. Okay? So anyway, I evaluate this. I do the same thing as before to compute this 165 knots, and the savings is actually not so impressive. It's down to 4 seconds, but the savings get better and better the bigger the knot is. So now I actually compute the Gompf-Sherman-Thompson 48 crossing knots using the extra fast Kaufman bracket program, and let's see how long it takes. So actually there is a little bit of, 6 seconds. So we went down from 10,000 years estimate to 6 seconds, and that's pretty good for 20 minutes or so of thinking. Why did I do that? Well, for several reasons. I mean, it's good to know that you can do things you can do things well, and then you can do things better. And like the improvement could be dramatic when you're doing exponential computations. And the second reason is that, people actually care about these values. You actually want to know this value. You would have never known it if you hadn't done this. If you hadn't, it would be, okay? And later we will learn how to compute, we will define and learn how to compute Chovanov homology, and the computation will be made faster by very, very similar tricks, and then it's, even more dramatic. Okay? So that's all for today.
Question about this dramatic improvement.
Yeah.
It seems strange to me that it could be so dramatic because if the number of terms in the polynomial while the front is still moving, that is bounded from above by the number of smoothings, and there are n crossings, then the worst case complexity should be the number of crossings times the number of smoothings. However, if you make the front very small, it seems like you can only improve this to the number of smoothings. Or am I missing something?
But the number, okay. Here's an estimate, okay? So suppose you have a knot, here is a knot, and it has n crossings. Okay? It turns out, so n is roughly the area of this crazy combination of crossings, right? Like suppose you put the crossings with fixed area, then n is roughly the area. Now, I pass the front through the widest part. The width of the front will be roughly square root of n. And in fact, you can prove it. This is provable. That you can always make a front that cuts the knot at roughly square root of the number of, or you can make a trajectory of fronts such that the front never cuts the knot at more than a square root of the number of crossings. Now, the original computation was complexity 2 to the n because there are 2 to the n smoothings. But here, below each front, so each front cuts the knot at only square root of n places, and so you need to look at roughly the Catalan number of square root of n divided by 2, ignore the divided by 2, it doesn't matter. And this is roughly 2 to the square root of n. So you've switched from complexity 2 to the n to complexity 2 to the square root of n, and that's a very, very, very dramatic difference. Well, we're already 2 minutes over time, so see you on Friday. There will
So
be
I have
homework
a
one.
question.
Yeah.
Yeah, so the number root n, does it depend on a particular PD diagram or any PD diagram at all?
Oh, it's not, root n is an estimate. Of course, for different diagrams, it will be a different number. But it's a bound. So you can show that if you have a knot with n crossings, then the maximal width through it will be about square root of n. Okay, so see you on Friday.
Wait, sorry.
Yeah?
Hey, like I kind of really don't get it at all because I don't understand why anything is like changing. Like we have the same number, like we're just ordering them differently. Like even if in say just in the first factor algorithm, like there's still this many crossings. So like why, like what has decreased? Like
Okay. It's getting late. So do not let me start the next class without explaining. Okay? Good. So see you on Friday. Bye.